and share it again. Okay. Is that okay? Yeah. So question is, maybe set ahead still will convert it to some value. Okay. So some value here. And how do you define? Oops, sorry. How do you define? What is the meaning? I'm sorry?
Within the model class, if x theta, whichever has the smallest scale divergence.
That's right. That's right. Yeah. Yeah, that's the answer. So remember, you can, even if we cannot really define true parameter, if the true model does not belong to the class, we can still define the point in terms of a Kullback divergence measure. So the short answer, I gave a more complete justification. Let me show you. I just want to avoid making mistake with the class. So actually I have an answer here. So okay, 11. Okay, let Gy be the true density function which does not belong to the model. Okay, the probability limit of Qn is this one, right? The probability, because what is Qn? Qn is a sample mean of the log density, right? And so it converges to what? Qn converges to this one, because the samples are generated from G, density G. Okay, so my point is Xi theta will converge to what? To converge to its expectation, of course, right? But when you say expectation, you are referring to some distribution. And the distribution is not belong to your class, but it is still a distribution. So let's call it G. Okay, so let's call it G. That is this one. And so then that means using the same argument in the lemma theorem, we want to maximize. So the maximize of this guy, sample version, right, will converge it to the maximize of this guy. And the maximizer of this guy is a minimizer of the Kullback Leibler divergence of G given F7. So that is the basic idea, but that's not really, has nothing to do with the missing data problem at all. So I just you can check later. Okay, other properties of the MLE: uncertainty normality, uncertainty optimality, Week's theorem, but that should be covered in the 542. So that's, I'm not going to talk about these technical details here. So let's move on. Now we are going to move on to a little bit different topic. So far we talked about model identification and maximum likely estimation, right? Another important concept is information, feature information. So first of all, we given the model, right? Given the model at y zeta, you can think about the log density and then partial derivative. So that is called the scope function, right? The gradient function. And then information function is gradient of the scope function. So partial derivative. So that is called Hessian. And then so if you so density function will as a if you have a density function you tangent, right? You have a tangent and tangent. So my point is the likelihood function should have a maximum. So it should have a maximum like this. And then that means locally, at least locally, it should be like a convex. So that means Hessian should be negative. So that we need to take the negative, to the Hessian in order to obtain positive number. Okay, so that is the base value. And then you can see this is actually kind of curvature, right? Curvature, how fast they change, the slope changes. So the information high, that means if curvature, changes fast, something like that. So that actually gives a smaller variance, right? Around the family. So we'll talk about that soon, but so this is the base concept. But one thing you can notice is the scope function and information function is a function of data and theta, right? Like likelihood. So it's a function of y and function of theta. And so that's why we use theta and y together. And you want to quantify some information, the variance or something like that. Then you want to get a number. So there's two ways to get numbers. One is to remove theta by replacing by theta hat. That is a completely function of y. Right? Another way is you take the expectation of the random variable and express it in terms of theta only. That's another, right? So you can see that if you take the expectation, the name expected feature information means that you take the expectation. Okay? The observed feature information means that so observed means data, right? The realized. So that means you want to replace the unknown theta by theta hat. That is the idea. Okay.
What is in 4.2, you have the derivative with respect to theta, the derivative with respect to theta t. What's the t for?
You mean the round? You mean?
Yeah. Gotcha.
I mean the key? Yeah, transpose. So, okay, that's actually, I should tell you this. So here theta is a column vector, p-dimensional column vector. Log f itself is a function, scalar function. So how do you really define a scalar function by vector? You can think it component-wise. So like after you apply column vector, partial with respect to column vector, this one is actually a vector, right? Same way you have column vector. So you cannot really apply partial derivative to column vector with another column vector. No, you cannot do that, right? But for each component, so for each component, you take the transpose, so row vector, then it becomes a matrix, right? This one becomes a P by P matrix. Yeah, there's a lot of some details going on behind all the formula, so that's a little bit, yeah. There's a little bit, make some, newcomers to digest. Feel more difficult, but that's actually advantage. I mean, once you are familiar with all these concepts, that gives actually that is your advantage because you are already, past that stage. So otherwise, everybody jump in, then life will be more tough, actually, end of the day. So anyway, feature information is only meaningful in the so the main original idea is to understand the curvature around the maximum likely estimator to quantify the variance, right? I mean, to quantify the uncertainty. So really, what is more relevant is around the maximum. And observable information is always positive. And observable information applies to one single data set. So that means because this one is based on the data, it only refers to the particular realized sample, while the expected information is actually taking the average. So there's a subtle difference. So we'll cover that later. But the main point here is that the expected information is not really relevant to the particular realized sample. Rather, it is more like quantifying the characteristics over all possible samples generated from the data. From the distribution. Well, luckily in the exponential family, we get this simple result. So in general, observable information and expected information are not equal, but sometimes they coincide, and that happens in the exponential family. Bartlett identities. Okay, so that is one of the key results we will keep using later. I believe that this is probably covered in the 542. So let me, rather than using the board, let me just use the script and just go through. Make our life easy. So go through the steps for the proof. Okay. So by the way, let me just first talk about the meaning. So it's really important. Scope function has a zero expectation. And variance. So scope function itself is a random variable. First of all, right? Scope function itself is a random variable. And zero expectation, and the variance is information. And why this is useful? Because later we'll come back to this again. But the point is that the MLE is a linear function of the scope function, but the coefficient corresponding to the scope function is the inverse of the Fisher function. So if you take the variance, then you have a inverse of Fisher information minus the variance of scope and inverse of the Fisher information. And so you get this one. And then the Bartlett identity basically says that this is equal to this. So you get cancellation. So that you end up getting this. So the variance of, so point is that variance of the MLE is approximately proportional to the variance of the scope function. But the proportion, the tangent, the coefficient for the scope function is actually inverse of the Fisher information, so that we have a sum. So this is actually sandwich formula, sometimes called sandwich form. You have a sandwich, you have a ham inside and bread outside. But here somehow you get the same thing. So we have a interesting result. So anyway, I mean, this is quite well known, right? I mean, MLE, variance of MLE is the Fisher information inverse, and that's actually used to derive the Rao-Kramer inequality. Basically says that MLE is aesthetically optimal, right? And so that's a good thing. But the key formula in applying this result, in obtaining this result, is this Bartlett identity. Okay. So should it be covered in 542, right? But 543, right? No? No? Okay. What happened to Iowa State? Okay. Well, I thought this is already, you guys already knew, and so that's why I want to simplify. But okay, the proof is not really difficult. So expectation of the scope function, okay, is what? Scope function is a log, right? Partial derivative of the log density. And then let's take a look at very carefully what is the log partial derivative of log density. That is actually, partial derivative of f divided by f y, right? So line by line is very okay. And then what is this expectation? The expectation here is you have an integration, and then you have this quantity times the density, which is numerator denominator, right? So you have this denominator disappears, cancels, and so you get this one. Okay. And then suppose, so once you obtain this, suppose you can change the order of the integration summation. Where mathematicians are very careful when it comes to changing the order. Statisticians don't. We just do it. Okay. So where many densities actually satisfied. So we just do it, and then the integration of the density is 1, right? So that means you get 0. Partial derivative 0. So that is the first result. Okay. So, and then second result. So originally the second result is what? Variance, right? So we just show this already. And now we are talking about this one. So first of all, here we are talking about the vector. So S is actually vector, random vector. So that means this one is actually a variance covariance matrix. Okay, so that's one thing we need to worry about in the beginning. But anyway, so then what is the variance? What do you mean by variance of the random vector, right? Zeta and y, where we need to express it in terms of expectation of S times S transpose minus expectation of S and expectation of S transpose, right? Because this is a P by P matrix. So this one is a P and P. So that becomes a P by P, right? And then this is a P and this is a P. Okay. And then this one is 0 already. We already showed this one. Okay. So that means to prove that this is equal to, we want to show this, right? We want to show information zeta and y. So that is our goal. But to prove this, because of this, and this is 0, so we want to show, we have only to show this guy is equal to this guy. Okay, so that is what we want to show. So that's what we want to show. Okay, and the right side here is that minus of the scope function of the partial derivative of the scope function is the information metric, Fisher information function. Okay. So we want this equality, and we have two options, right? To solve this. One is use this one to derive this one. Or we use this one and derive this one. Okay? Which one is easier? It's easy to start with a complex thing to simplify, rather than from simple thing to make it more complex, right? So this should be more complex because it has more data. So anyway, I'm going to start from here. That's totally irrelevant. So we need to show this, but what we are doing here is, remember, to prove first one, what we did is essentially use this topic. So you can view this way. So density integration of density equal to 1 is equivalent to the expectation of scope function equal to 0. Okay, it's actually totally equivalent concept. Okay, now we are here to prove this. We use this. This is actually identity, right? As a function of zeta, this is identity, and take the partial from this identity, and then notice that in expectation we have a zeta here. So actually there's a subscript zeta already. So there's two functions, zeta here and zeta there. Zeta originally in scope function, and then another zeta in computing the expectation, and then apply the chain rule. Okay, so if you apply the chain rule, and so you get this one, and then the first one is expectation of the final scope function. Second one is more tricky. So do you guys have a clue of how we get from here to here? Huh?
This is the definition of the scope function.
Right. So scope function. So yeah, maybe I should have put one more line here that will make you guys feel better. Scope function of zeta y is what? Partial derivative of the log f. So that is actually what? Partial derivative of f divided by f, right? So here I'm talking about this guy. So this guy is the numerator. So the partial derivative of f is equal to the score function times density. Okay, so basically this guy is a score times score derivative. I mean score time times density. That is this perspective. So I think that it gives the proof for the theorem 2.3. I think that's the main. Okay. And then the details you can check the script, and then that actually gives us some meaning discussion about it here, but I think I will stop here, and I will make a short recording, like a 15 to 20-minute recording as a makeup. So to give a full discussion of this result and some other topics, advanced topic, and that you guys might interested. But this is totally not really important in our understanding of the missing data problem. I just want to present it to cover the minimum background knowledge of mathematical statistics. So next week, so first of all, I will finish up all this by recording, and if you have time and curiosity, you are welcome to attend. Otherwise, that's fine. We'll just move on to the next. So move on to missing data next Tuesday. Okay, and have a good weekend.